the sail on a boat. Okay. It says, let R be the region in the first and second quadrants. That's up above. Okay. So first and second quadrants. Here's the line y equals 2. What does this look like? Okay. It's not a parabola, just for the record. Okay. Yeah, and so it looks like what? Okay. Below by the horizontal line, above by that, so we have something that looks like this, right? Yes, no? It's asymptotic with what? Zero? As x goes to infinity, y equals 0, right? Okay. And then, so what happens at y equals 2 here? Right? Isn't that the other line? Y equals 2. Does it cross? Okay, it does cross. Do we know where? -3 as well. Okay. If you can't find those analytically, you know, setting this equal to 2 and solving it, then at least find it using your second calc, right? Your intersect. Okay. So we have this region. Okay. So what does the area look like? We got an upper curve and a lower curve. Area equals what? What are my upper and lower bounds? -3 to 3. What's my bigger curve? 20 divided by 1 plus x squared. What's my littler curve? 2. Make sure you bracket those off. What do I need at the end? dx. Okay? That is an f-int. Okay, I know this is a calculator question. It's on the calculator part of the test. So, getting an f-int, what do you get for an answer? Okay. Bless you. 126. That needs to be in brackets. Denominator needs to be in brackets. If you're dividing and you don't have that fancy calculator that gives you a top-bottom fraction, you just have the fraction bar, the slash, then the bottom better be in brackets. What do we get? 37. Yeah, 37 points. Give me 3 decimals. 962. Wow, I didn't even write that. There we go. 962 square units. Okay. And then I just realized something about the volume. We can't. Wait a minute. No, we're learning this today. Shoot, I should have read that more carefully. Yeah, because it doesn't go. What happens when we rotate this about the x-axis? Let's talk about this a little bit. Yeah, exactly. When we rotate that about the x-axis, since this region doesn't come all the way down to the axis of rotation, when we rotate this, we end up with this gap right through the middle, almost like somebody took a drill and drilled a hole right through the middle. We're going to deal with that today. Okay. In fact, it's a nice lead into this question. How would I find the volume of that ring? have to do? Tom?
Take the volume of the whole thing and then take the volume of the whole and subtract that.
Exactly, right? Does anybody remember what the volume of the whole thing was from yesterday? No. Anybody remember that volume, the whole volume from yesterday?
Wasn't it 9 pi?
Was it 9 pi? Can somebody look that up? For some reason I remember 8 pi, but I don't think it was 8 pi. Was it 8 pi?
Was 8 pi.
Was it 8 pi? Okay. Okay, so we know the outer volume was 8 pi units cubed. Catch up to me eventually. How about the inner? How are we going to find the inner? Yeah, this radius here, I tried to do a somewhat decent job. This radius is 2 inches. So how are we going to find that volume? Yep, pi r squared times the height, which is, you know, the length of the cylinder here because it's on its side. And my radius is how much? Okay. So I'm beginning to think it wasn't 8 pi, but okay. Yeah, I'm looking at that going, it can't be 8 pi then. Okay, so this was 36 pi. There we go. Okay, so pi, radius is 2 squared, height is 4. Yep. So what do we have here? 16 pi. Okay. So we have 16 pi units cubed. And so now that we know that represents a hole or a void or an absence of material, however you want to call it. So what do we have then for that ring?
36
Yeah. So the volume of that ring is going to be your 36 pi minus your 16 pi. Unit 20 pi units cubed. So we had the volume from yesterday. We had to recalculate the volume of the whole, and then we can subtract the two. So in terms of integration, guess what's going to happen? We're going to have to take a look at that integration of that function that creates the outer surface, the bigger portion. I'm going to have to take a look at the function that creates that inner surface, that littler portion, and subtract the two. Okay, so what that's kind of looking like on that free response. It's kind of looking like upper curve minus lower curve. So if you turn to the next page, in order to evaluate, and we call these washers, because you've ever seen a washer, right? It's got a hole through the middle. Okay, so we call those washers. And so if we want to find the volume of that solid figure that's got that missing material in the middle, then what we're basically ending up doing is we're saying, let's take that outer radius, and we call the outer radius big R. Let's take that outer radius and do our pi r squared with that. And then let's take our inner radius and do our pi r squared with that. Okay? And so we get this this shape of an object that is that's got that missing center. And so we're gonna look at this shape. We're gonna look at a parabola with a line that cuts through it. So we've got this kind of I don't know what you want to call it, but we've got this enclosed shape here, and we're going to revolve that not only around the x-axis, but we're actually going to revolve it around an axis above it too. And we'll take a look at those shapes. So when we take this and we revolve it around the x-axis, we're going to have this area here where we have that hole through the center. So really we have then something that looks like that on the bottom as well. Okay. So we're going to take a look at those two functions, and we're going to, like I said, we're going to revolve them around two different, the x-axis and then a line. I think I picked y equals 5, so right at the tip of that shape. Okay, so I do have here's the shape. So we have this line, x equals 3, and we have this parabola x squared plus 1. And it's too far away. Bummer. Okay, and I also have here, if you take that Google URL, you have another GeoGebra file that you can work with to generate these solids. I've got that file pulled up here. So if we take this shape, and you can kind of see, if I revolve this here, there are the two functions. So we set those two functions equal to each other. And we can find those points of intersection. So that's the first thing we're going to do on this example here. So if I set these two functions equal to each other, x plus 3 equals x squared plus 1, how do I solve that? Yeah, we have to recognize that as a quadratic, right? We have to factor it. So we're going to put everything, I have my x squared over here, it's already positive. I'm going to move everything over to that side. So I have x squared, I'm going to bring over my x. So it's going to be minus x. I'll bring over the 3 is a minus 3, so add that to the 1, I get a minus 2, okay? That's algebra stuff. And what does that factor into? You can probably pick it right off the screen. Yep, exactly. So we have x minus 2, x plus 1. And then so we can see those roots, right? X equals 2, x equals negative 1. So we intersect over here at negative 1 and positive 2. Okay, what is that setting up? Finding those points of intersection sets up what? Yep, your upper and lower bounds. So we're going, as we revolve this out of the screen and then back into the screen, so kind of into the chemistry room, we're going to stack those washers up, starting at negative 1, going to positive 2. So remember, yesterday I said it was really important to be able to set up that incremental rectangle. So this incremental rectangle is going to go between the upper curve and the lower curve. Okay, so we know it's a dx, exactly, the width is dx. And then we identify the top of the rectangle. The top of the rectangle is on what function? The line, right? So that's our big R of x. It's the farthest away from your axis of rotation. It's your biggest radius, so we call it big R. Okay, and then the bottom of the inside of your washer is on that parabola. So that's our little r of x because it's closest to this axis of rotation. Okay, so we have to look at everything relative to what axis we're rotating this about. Okay. So going back to that GeoGebra file, Here's the GeoGebra file. If I go ahead then, I'll go ahead and get this back kind of into 3D. So there we are back into 3D. And I'm going to go ahead, I lost my play button for some reason, but I can go ahead and just spin this around 360 degrees. So as I build this and I spin this around 360 degrees, I can see that the inside of that three-dimensional shape is that quadratic, is that rounded surface. So that rounded surface, we can kind of start to see the hole through the center there. So that rounded surface is on the inside and this flat surface is on the outside. So as I spin this around, so as I go into this window and I spin this around, we can start to see the hole through the center. And we can see that inside surface is curved, the purple surface. So if we look at it from the side, we can see we kind of have this bowl shape with a curved surface on the inside. Okay. So we have that curved surface. So we're going to go ahead, let me just kind of set this up to sort of be somewhat 3D-ish. Okay. So we're going to go ahead and integrate that. Okay, so we have our limits of integration. So we know we're integrating from -1 to 2. And we're just revolving that slice, so we're generating that circle. So our larger radius is the line. What was the equation for that line again? X plus 3 quantity squared. So remember, we have to square the radius. The biggest mistake is forgetting to square the radius. So our radius is x plus 3. In other words, from the axis of rotation, we go up to that function. So that's the y value of that function. And then we're going to subtract the inner radius, which is the quadratic. So we're going to subtract the, what was that, x squared plus 1? X squared plus 1, and then we have to square that too. Remember, the x squared plus 1 is just the radius. Okay, so that's from the axis of rotation up to that quadratic. Okay, so that little r, and then we can close that off and we can have a dx. Okay, so that little r is just this value here. There's that. So if you notice, from the axis of rotation to the quadratic, we're not inside the shape, we're underneath it. That's why we're subtracting it out. Okay? And then our big R is from the axis of rotation out to the function. Okay? So the axis of rotation out to the function is that line, and then we have to subtract the stuff underneath the parabola to get that enclosed shape. And this is where the operating system that actually shows you the integration sign is really handy. It works a lot nicer than the old operating system in your graphing calculator. So what do you get then when you integrate that? And again, this is, we could FOIL this and integrate it, but really it's an F-int. Okay, these are just, and you know, if you are going to FOIL this out, remember x plus 3 is not x squared plus 9, it's x squared plus 6x plus 9. Right, we had to FOIL that whole thing out. Okay, so 70, okay, did you include your pi? You did. What if you divide pi out? Just curious. Tyler's getting 73.513. 73.513 units cubed. You know what? What is it as a fraction? I'm having Tyler get this in terms of pi. So he got this answer with his F int, and then he divided by pi and used the pi key, and he gets 117/5 times pi units cubed. Okay. So, this would just be in terms of pi, and either answer is acceptable. But, you can see that as if we would FOIL this and integrate it, we would end up with a lot of, x cubed over 3s and x to the 5th over 5. So we would end up with some fractions that we'd have to add together. Okay? You doing okay so far? Okay. So our next task then is, and I'll give you a second to kind of get caught up on the, is that up enough? I'm getting the notes down. The next task then is to take this same shape and revolve it around a different line. So revolving it around a different line means we're moving the axis of rotation. So we're changing how far our top of our rectangle is away from the axis. Does that make sense? As that axis shifts, the top of the rectangle shifts. So if we look at this scenario, I'm going to have the axis of rotation be right here, right at the tip of that shape. So now my axis is right here. I'm going to spin it this way instead of this way. I'm going to spin it up here. So is there going to be a hole going through this one? No. Because, why not? Yeah, we've got this touching the x-axis here. Okay, so we don't physically have a hole, but when I rotate this, so if I go back to the GeoGebra file, and all I have to do is change this axis of rotation up here in the upper left-hand corner. Okay, so I'm going to change that to a y equal to 5. And so if you notice down here in the lower left, my axis of rotation is now different. Okay? And so if we come over here to the 3D, and let me just reset my theta at 0. So we have this axis of rotation here. It's going to be y equals 5. We're going to flip it this way. So as we flip it that way, I think I might need to zoom out first, just a little bit. And I think I might need to move this down a little bit, just to fill a space. As I rotate it about that axis, oh, shoot. My program's not working right. Bummer. Let me turn off some surfaces here. Get rid of that. Gotta change that. So we get this. Unfortunately, I have to turn off my surfaces. I'm still working the glitch out of my programs here. We get this shape here. So if I revolve this enough times, I should be able to kind of color that in. So as we look at this shape, we can see that the inside of it Looks like the shape of a what? What is that orange shape on the inside? A cone, yeah. And on the outside, we can see this kind of curved surface on the outside, and then we have this cone on the inside. Okay, yeah, I know it's not as pretty as the surface, but if we look inside that shape, if I rotate it enough to look inside the shape, we don't have a hole in the center anymore. That comes to a point where that cone is. Okay. So this gets a little tricky because we have to find our big R and our little r. And everything is relative to the axis of rotation. So our big R goes from the axis of rotation to here. Our big R is now the what? Going to what function? The parabola. Try to stay focused on calculus here, people. Read on the home stretch. Okay? So that big R goes down to the parabola. Now, is it just the value of the function? Or is it something else? How do we find this distance? In fact, actually, technically, these probably shouldn't even be labeled big R and little r. If this is big R, and this is the function it goes to, that function is always measured from the x-axis. Is that the height of the rectangle? Yeah, it's 5 minus that. Exactly. So this big R of x is really 5 minus the function x squared plus 1. So that distance from this line to that point, if this is x squared plus 1, right? Because functions are always measured from the x-axis. So if that's the function, then from here to there is 5 minus the function. So that's the radius that's going to be spun. What about the little r? Exactly. So this little r, if this is the function of the line, so if this is x plus 3, then this is 5 minus x plus 3. So little r equals 5 minus x plus 3. So let's simplify those two expressions before we put them into the integral. So simplifying big R of x gets us what? Yeah, right? 4 minus x squared, that's a little easier to put in to your calculator. And simplifying little r gets us what? Oh, thank you. Tyler's correcting me here. Right, 5 minus the function means I need brackets. So he's saying 2 minus x. He's right. If I would have forgotten those brackets, I would have had 8 minus x, which would have been wrong. Okay. What about our limits of integration? Are we dealing with a different enclosed area? No. So what about our limits? Our lower and upper limit? Still the same, right. So we still have from -1 to 2, pi. What's our big R? 4 minus x squared. Don't forget we have to square that. Okay, 4 minus x squared is just the radius. And then we have to square the radius because we are generating circles in these things. And then our little r. Two minus x quantity squared. Okay. So what happens when you stick that into F int? And again, we could FOIL that and simplify it. We're probably going to get some fractions, though, when we do that. But that's definitely an F int. I got something up with the calculation there, too. So we're going to need some brackets here, definitely. So I put down a bracket, 4 minus x squared, close the bracket, hit a squared again, minus another left bracket, 2 minus x, close those brackets, hit my squared, comma x, comma negative 1, comma 2. And then I didn't even put the pi in yet because I like to see that decimal, because that's going to help me for WebAssign, because you know WebAssign, if you have a terminating decimal, it's going to have you enter it as a fraction. So this gets me 21.6. So I know I have 21.6 pi units cubed, which would be fine for an answer on the test. I'm going to do a math fraction. Just, yeah, 108 over 5. Pi is probably what WebAssign is going to want to see. Units cubed. Okay. Okay, so on tonight's homework, you have, I think, like 2 questions around washers around an axis, maybe 3 questions washers around a line, something like that. Okay. Anything that's polynomial above a degree of 2 is probably going to be an F int on a test. Just kind of giving you a rule of thumb. This next test next week will be a more free response and multiple choice. I might have just a few multiple choice questions, or not many of them from this content. So you'll have 2 or 3 free responses for calculator and no calculator. No calculator free responses will be really grading your setup. Okay, so appropriate brackets, your dx, your integrand, all that stuff. Brackets around the pi. Like here? Yeah. No, you can leave it there. Or you can pull it out front. Or you can have it in here. Or like you have brackets here. You want these guys? Yeah. Everything that's got pluses and minuses, that wouldn't be wrong to do that. That's fine. If you didn't have these red brackets, I don't think they would take a point off. I really don't. Okay. So any questions about that? All right. We've got the rest of the time to work on WebAssign. And I think I need to extend yesterday's, so I'll do that right now.